All right. So when we're talking about algebra, every number that we use in algebra is inside of what's called the real number system. And the real number system is every number that is real, because believe it or not, there are numbers if you end up taking algebra 2, you will end up learning that there are numbers called imaginary numbers, and no, that's not a joke. So there's actually two separate systems and types of numbers. One of the systems, the one that we will be using, and the one that you use the vast majority of the time in all of math, is the real number system. But there are some, once you get to algebra 2 and beyond, there are some numbers called imaginary numbers, which is why we define these as real numbers. Awesome. I do not plan on putting the notes in the gradebook, no, but because our tests are open notes, it's always a good idea to keep good notes, because you can always refer back to those on tests. And I shouldn't just flat out say no. I don't have any plans to be grading your notes. But if that's something that ends up needing to happen, then I might. But at this point, I do not have plans to be grading your notes. Because those are for you. All right. So the types of real numbers that we will be dealing with. So, second here. Okay. So real numbers. We have some symbols for these as well. So the real numbers are, we're gonna just kind of use a capital R. And actually, when I learned this in school, the real numbers actually had, like, instead of just like one vertical line for the R, there's two. That's how I learned how to write real numbers. So if you have two vertical lines and then complete the R, the capital R, that symbolizes real numbers, which basically just means all numbers. For all intents and purposes, this includes all numbers. Like I said, there is that other category called imaginary numbers. We don't get close to dealing with that in this class, so we're just going to call this all numbers. Now, within the real numbers, there is this large category over here called rational numbers. And so we're basically splitting real numbers into different categories. There's two main categories. There's rational numbers and there's irrational numbers. Within rational numbers, there are three other categories of numbers. And so we're going to start down here at the bottom with natural numbers. Natural numbers, we're going to use a capital N, but just like with the R, I'm going to do like a double line. Oops, you can't even see that. Just like with the R, we're going to do a double line, capital N. And these are your counting numbers. So if you're counting values, what's usually the smallest number that you start with? 1, exactly. So the natural numbers are 1, 2, 3, 4, and so forth. They are positive whole numbers. So natural numbers, I'm just going to write this underneath here, positive whole numbers. Those are the natural numbers. It is the most limited category of numbers that we have. Even though it's an infinitely large category, it's the most limited category that we have, which sounds a little weird, right? Because there's no limit to the number of counting numbers. We can count up as high as we want to, but we are limited to just positive whole numbers. The whole numbers, which is weird because natural numbers are whole numbers, and then there's whole numbers, which are whole numbers. And we're going to do a W for this one, and we'll kind of do a double diagonal for that first one. And the whole numbers are all of the natural numbers. So what we're doing is we're expanding. Every one of these gets bigger in terms of the numbers that we include. So every new category includes every number from the previous category plus some new numbers. Does that make sense? Yeah. That's it? Yeah. So if we think of numbers, like all real numbers is like, I don't know, the state of Oregon. All the people in the state of Oregon could be like all the real numbers. Basically, the natural numbers are everybody here in this room, right? We're all in this room, which is in the school, which is a little bit bigger than this room. So that could be like a whole numbers, which is in the town of the Dalles, which could be a little bit bigger, which is like the integers. So everything that is in this category here exists in this next one here. And everything in the whole numbers exists in the integers, and everything in integers exists in rational numbers, and everything in rational exists in the real numbers. So it's going to just get bigger and bigger as we go out. Now the whole numbers are a little bit weird because there's only one extra number in whole numbers versus natural numbers, and that extra number is 0. So the definition for whole numbers would be the natural numbers and 0. So and instead of actually writing natural numbers, we can just use the symbol for it, which is why, that's why in math there are so many symbols, is because it allows us to write fewer words. And so once you know what those symbols are and what they mean, you can just use the symbol instead of writing out the words. And so I'm just going to use the symbol for natural numbers instead of writing out the words for natural numbers. So the whole numbers are all of the natural numbers, all of your regular counting positive numbers, and 0. Integers. We've talked about integers before. We've used them before. What are they? I've mentioned the definition a few times. Anybody remember? Positive and negative whole numbers, exactly. So this would be positive and negative whole numbers. And I'm actually going to use whole numbers, the words, because whole numbers does the category of whole numbers doesn't include negatives. So I don't want to use that symbol for it. But basically we're expanding it because integers includes 0, 1, 2, 3, 4, 5, all of those numbers that we talked about already, but also all of the negative whole numbers associated with that as well. And so for integers, this is where it gets a little bit different. We're going to use a Z for this one. I'm going to do a Z with a double line kind of on the diagonal. And the reason we're using Z and not I is because we have another one up here that starts with an I, and that one gets the I. Integers doesn't get the I. Integers gets a Z. And so integers would be, I don't know, let's say -2. I'm actually going to do a ... before that because I want to imply that everything that comes before -2 is also included, which is true. So this one has numbers on both sides that go infinitely far. Whereas natural numbers only move in an upward direction, whole numbers only move in an upward direction, in a positive direction. Integers move in a positive and a negative direction. They kind of go in both directions forever. And then rational numbers. There's a definition for those already. It's written right above where it says rational numbers. And we've actually seen this definition already. This definition was, I think, back in our first day of fractions. Yeah, there it is. We already have a definition for this. Any fraction or any number that can be written as a fraction. And so this definition is a little bit more specific. It says all fractions and decimals that end or that have a repeated pattern. And the symbol that we use for this one, we can't use R because we already used R for real numbers. So we're going to use it's actually a Q. So I'm going to do Q with a line in it like that. So that would be rational numbers. By the way, these symbols, I'm not going to make you memorize those. I mean, aside from the fact that you have access to your notes whenever you want. These are not things that you will be needing to know, these symbols, as we go throughout this class. The categories of numbers, definitely a good thing to know. The words for these numbers, rational, integer, whole, natural, irrational, and real, those are good things to know. The symbols, it doesn't really matter if you memorize those or not, but it could make things a little bit easier when you're writing these out to use the symbol as opposed to the word. So rational numbers, let's see, the examples that the P gives is like 1/3. So that's a fraction. If it was but this turns into a decimal that repeats, right? It's 0.3 repeating, but this is rational. So anything that could be written as a fraction. And I think the specific mathematical definition says a quotient of two integers. Quotient meaning number over another number, division, integers meaning positive or negative whole numbers. It's like 1/3. 1 is an integer, 3 is an integer. This is a quotient. So we don't have to get super technical with that, but that would be an example of that. Negative 0.67 would work. The square root of 16 is also a rational number. And there's just so many options that, I mean, there's no way to even approach how many there actually are. All right. And then the last one we're talking about are the irrational numbers. And it kind of looks like the Roman numeral 2 because the double line high. And it gives us a definition as well. And it says that irrational numbers are numbers that have decimal values. They're all decimals. Every single one of these can be written as a decimal. However, these decimals, not only do they never end, some of these over here don't ever end, but they repeat. These ones over here, they never end, and they have no repeating pattern. So it's just like a jumble. Can anybody think of the most commonly used irrational number? Yeah. Pi is by far the most famous of all the irrational numbers. We all know it as like about 3.14 because practically speaking, 3.14 is enough to be accurate. But technically, it goes on forever. It does not have any repeating patterns. And so far, I think they've got, I mean, there are supercomputers dedicated to just keep calculating the next decimals for it. And we're in like I mean, it's in the trillions at this point in terms of how many decimal places it's been found to. Pi was actually proved a long time ago. It was proved to be irrational, meaning there is no argument to the contrary that could suggest that it is rational. This is a little bit weird to think about. But for example, pi is definitely one of them. It is the most common one that we will use. Other irrational numbers are any, first of all, square roots. Are people familiar with square root? This here? I see yes, I see no. Square root just means the opposite of squaring something. So like if you square a number, you're multiplying it by itself, right? Square rooting a number is thinking about what number multiplies by itself to equal that number. So what would this be? What number multiplies by itself to equal 16? 4, exactly. So the square root of 16 equals 4, which is why this is rational because it turns out to be just a whole number. However, anytime you have a square root that does not equal a whole number value, it's going to be irrational. So for example, the square root of 2. Think about that for a second. And you might be thinking to yourself, well, it's 1, right? And no, because if you take 1 and you multiply it by itself, you get 1. And if you take 2 and you multiply it by itself, you get 4. So if you try to think about what number multiplies by itself to equal 2, it's like it's 1.4 something, but it's irrational because it just goes on and on and on forever and it never repeats. Another example would be the opposite of the square root of 101. That would be like negative 10 point something, because 10 times 10 equals 100, but 101 is just a little bit more than that. So, all right. So the next thing we're going to do, and I also want to point out, Natural numbers are whole numbers. Natural numbers are integers. Natural numbers are rational, and natural numbers are real numbers. Integers are rational numbers. Not every rational number is an integer. Meaning 0.67 or negative 0.67 is not an integer because it's not a whole number, but it is a decimal that stops, and so therefore it is rational. So we have to think about these different categories. So basically, if it's natural, it's all of these other ones. If it's a whole number, it's from here all the way up. If it's just a rational number, it's just a rational number. And then over here, irrational, notice it's completely separate. If we categorize a number as irrational, that is the only way it can be categorized. Whereas over here, there are multiple things that we can categorize it as. Let's start off here with number one. So number one, we're just going to name all the subsets. We'll just do the symbols to make it quicker. If it's a positive whole number, that means it is natural, whole, integer, and rational. It's all of those. We do not need to put the R for the real number symbol here because everything that we're dealing with is a real number, so there's no point in even doing that. So we don't have to use the R, but we do have to use every other one of those. So it is natural. It is a whole number. It is an integer. And it is a rational number. So if it is a natural number, it automatically is part of all four of those categories because the most specific type you can get means that it's within everything else. It'd be like us here, like I said earlier, we are in this classroom 209, which means that we're also in the school, which means that we're also in the Dalles, which means that we're also in Oregon. But you can be in Oregon without being in the Dalles or in this school or in this classroom. Negative 11. So first thing you should do is look for the most specific subset that you can find. So where would negative 11 fall? Is negative 11 a natural number? No. Is it a whole number? No. Is it an integer? Yeah. So we'd say integer and rational for this one. Because it's an integer, it has to be rational. So we say integer. And we say rational. We're using C and Q for that one. All right. Number 3. Can this fraction be written as a positive whole number at all? Is that a possibility? No. So it's not natural, it's not a whole number, it's not an integer. Right away, we knock off 3 of those. Because it can be written as a fraction, though, because it is a fraction, that means it has to be at least rational. So that's what it is. So that one just fits into the rational number category. Number 4, the square root of 21. Now, if we think about square roots, and we'll end up using calculators for a lot of these as well. And at this point, you are welcome to start using calculators. Please do use an actual calculator, though. I have a lot over there. We're not going to grab them yet, but if we think about how numbers multiply by themselves, we looked at the square. We talked about the square root of 16 a minute ago. That's 4 times 4. What does 5 times 5 equal? 25, which is more than the square root of 21, which means that the square root of 21 is somewhere in between 4 and 5, which means that it's not a whole number value. And I mentioned before that any square root that isn't a whole number value is irrational. So we're going to say irrational for that one. And if I were to type this in here, if I were to type in the square root of 21, there it is. It's just a random assortment of numbers, and it can't show the whole thing because it's a pretty simple calculator. And it only goes to however many decimal places that happens to be. So square root of 21, irrational. Number 5, 0. Is 0 a natural number? No, because these are only the positive counting numbers. It is a whole number, though. So that means if it's a whole number, that means it is also an integer, which means it's also rational. Okay. How about this next one, number 6? What do we think? Rational? Okay. What is this? What is the opposite of the square root of 9? What is the answer to this? -3, right? Because 3 times 3 is 9, and then the opposite of that would be -3. So it's not a natural number because it's not positive. It's not a whole number because it's not positive or zero. Is it an integer though? Yeah, so it's an integer and it is a rational number. So integer and rational for number 6. How about number 7? What does that equal? Number 7, what does that equal? It's 2. And because it's 2, that means it's natural, whole, integer, and rational. So just because it's written as a fraction initially, doesn't mean we just go straight to rational. If it can be simplified into a regular whole number value, then it can be included in, or it should be included in a lot of other categories. So we get natural for this one, we get whole numbers for this one, we get integers, and we get rational. Number 8, we should know this one already, right? We already used this one. What is it? Irrational. Yeah, that's our famous irrational number. Is that? Yeah. How about number 9? The line means what? The line over the decimal place means what? It repeats, right? So it's a repeating decimal. Okay. Where do repeating decimals fall in? Rational. Yeah. And that's it for that one. That cannot be written as a whole number because it's a decimal. It can be written as a fraction though, which would be 5 1/3. Which means it's rational because the decimal does repeat. All right. Now this next one, it's a little bit, maybe a little bit more challenging in terms of how it looks, but what number multiplies by itself to equal 144? What is it? 12, yeah. 12 times 12 is 144. So this is 12 divided by -3. What does 12 divided by -3 equal? -4, yeah. So this kind of complicated looking thing is actually equal to a negative whole number value. So where does that fit in terms of the categories? Is it a natural number? No, because it's negative. What about whole numbers? I think no again, because it's negative, right? Is it an integer? Yeah, it's a negative whole number. So it is an integer. So we're going to use Z. And we're going to use Q because it is rational. How about number 11? It's a decimal. It doesn't repeat, but it does stop. So rational, yeah. So Q for number 11, because you can't write that as a whole number. And then number 12, the square root of 17 is irrational. However, we know a rule for division that if you divide anything by itself, you get what? 1. Anything divided by itself, even if it's 2 irrational numbers divided by itself, the answer is still 1. Unless it's 0 over 0, I should say. But we get 1 for that, which means it's natural, whole, integer, and rational. That one's a little bit funky. So natural, whole, integer, and rational. All right. So far, just kind of categorizing some things. And from here, we're going to go ahead and move on to the next page. Are there any questions so far? Are we kind of seeing how this works, how we can expand and kind of limit which categories we're talking about here, hopefully? This is another way of looking at it. We just have ourselves a little diagram here. So it says, place the letter of each value in its location in the real number system below. So we're going to get as specific as we possibly can. So for example, A is a positive whole number, which means the most specific we can get is natural numbers. So we're going to place the letter for it down here. So A goes in natural numbers. And we don't have to put A in whole numbers because natural numbers, as you can see here, is contained within whole numbers, which is within integers and rational. So, and then this whole thing over here, I'm going to write real in the upper right-hand portion of that box because it doesn't actually say real numbers anywhere. How about B? What does negative 36 divided by 12 equal? Negative 3. Good. So negative 3 would make it a what? Integer, yeah. So we're going to put negative 36. Oh, no, we're not. We're going to put the letter B. Sorry. Place the letter. I'm going to circle that for myself so I can follow the directions. All right. How about C? What number multiplies by itself to equal 36? Is it a whole number? Yeah, what is it? 6. And because it's a negative 6, it's not a natural number. It is a, or an, it is an integer. So C, so B and C go in integers. D, we know this one. What is it? Irrational. So letter D goes in irrational. E, 6.48. Where does that go? Rational. So E goes up in rational. F, negative 2. What type of number is that? Integer. So F goes in integers. We got 3 of them in integers. We don't have any whole numbers yet. What about G? Be careful on this one. It's not 5. What number multiplies by itself to equal 10? Do we know? Do you know it off the top of your head? If the answer is no, then it's probably irrational because 3 times 3 is 9, right? The next whole number that multiplies by itself is 4 times 4, which is 16, which is a lot bigger than 10. So that means that this is somewhere in between 3 and 4. And since we don't know what it is, it's going to be irrational. So G is irrational. H. Whole numbers. Yep, H goes in the whole numbers. There's our first one for whole numbers. I, 2 1/6. It's a fraction. It's not a whole number. Therefore, it is rational. Yeah. Let's see. Negative 0.7. It is a repeating decimal. It's not a whole number, which means it's rational. Yeah. Okay. So J goes in rational. And then this last one here, the square root of 4 over 81. Now, again, this is not math that we've done yet. However, if you think about what the square root of 4 is, what multiplies by itself to equal 4? 2. So this is going to be 2 over what multiplies by itself to equal 81? 9. So 2/9. So it does simplify to equal 2 whole numbers as a regular fraction, which means it is what? Rational. Yep. So K is rational. Because 2/9 is a rational number. Okay. Next one. Which expression does not name an integer? Okay, so which one of these is not an integer? Is it A, B, C, or D? So 0. Is 0 an integer? Is it a positive or negative whole number or 0? Yeah. So C is an integer. Okay. Which one is not an integer? Negative 15, that's a negative whole number. So yeah, C is a whole number, 0. D, 12 divided by 6 is what? 2, which is a whole number. What about B? Is that a whole number? Positive or negative? Nope, that's a fraction, so B. Let's see, which of these is irrational? On number 2. Irrational. Repeating decimal, that's rational. 2/3, that's rational. So it's one of these two. It's B or D. So do we think it's B or do we think it's D? Because these are both square roots. What do we think? B? D? Square root of 3 minus square root of 3. Anytime you take a number and you subtract it from itself, what do you get? 0. Any number minus itself is 0, which means that D is rational, so it's got to be B again. So B is irrational. Square root of 75. What number times itself equals 75? I don't know. It's in between 8 and 9, but I don't know what it is. All right, which one of these is not a whole number? This one should be the easiest one so far, I think, because whole numbers cannot be. Well, 18 divided by 3, though, can it be written as a whole number? 18 divided by 3? It's B, because whole numbers, the set of whole numbers, those aren't allowed to be negative. So anytime you see, so there's a negative there, so that can't work. So B, 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 all right. Which of the following, oops, sorry, you couldn't see those. Which of the following is a true statement? -9 is a whole number. Is that a true statement? No, that's an integer because it's negative. 0 is a natural number. Take a look at our list of natural numbers. Is 0 a natural number? No, okay. 2/3 is a rational number. Is that true? Yeah. Square root of 25 is irrational. Maybe you're thinking yes, but at the same time, you also look and you say, okay, what number times itself equals 25? The answer is 5, which is definitely not irrational. So D, that is true. All right. Which of the following statements is false? Okay, looking for a false statement here. All real numbers are rational numbers. Is that true? No, because a lot of the real numbers are also irrational. So not all real numbers are rational. So that's our false statement. A is false. Let's see. All natural numbers are integers. So every natural number is contained within the integer. So that is true. Every integer is a rational number. That is true because integers are within the rational numbers. And then every whole number is a real number. Well, that's true because every number that we use is a real number. All right. How about this? Give an example of a number that is a whole number, but not a natural number. By the way, there's only one option for this. 0. Yeah. The only option that we have for number 6 is 0. Because the set of whole numbers is all of the natural numbers and 0. So it's the only number we can write for number 6. That's it. Number 7. Give an example of a real number that is not rational. So an irrational number. What's the most popular irrational number? A number that's not rational. What about pi? Give an example of a rational number that is not an integer. So basically, give me a decimal or a fraction that can't be written as a positive or negative whole number. Yeah, 0.77 repeated. I like it. Great. You do a fraction as well. You do like 3/10 or 1/3 or anything like that. All right. That is it for our notes. So your assignment looks pretty much exactly the same as what we just did. I'm going to hand this out. I'd like you to start working on it. If you have questions about your test, let me know. We can take a look at it. We can talk about it. If you haven't started the test yet, though, please make a plan to come see me this afternoon to get started on that. Because that means we need to get going on that as soon as possible. No, because these numbers are different. Attached. So we put A down here because 7 is a positive number, which means this is not a positive number. We would go in 4 because to be natural, it has to be positive. And series is not positive word. Yeah. Get A because it's a decimal. It's not a whole number. That's what I did. Stop. What do we say about it? Yeah. Here's our it's like a negative number. It's a negative number. Yeah, that's negative 3. Yes. In a small sense. No, don't worry about writing a real number sign. Since every single number that we use is a real number, then it automatically is real. Remember that I haven't gotten attendance in yet. I'm going to get that in here quick. Let's see. All right. So if it's going to be regular fraction, then it would be rational. If we do regular fraction, that's the same as this right here. So we're fractioning. So 1/10 is 76. One number times but it's under square root. So this is the only reason this is a whole number is because the square root of 49. If the square root equals a number, then it can be written. If the square root can't be written as a whole number or make a fraction. That's because the square root of 35, no, the square root of 36. Yes. It just has to do with the way sometimes capital letters, like the capital letters for like R, I, other capital letters can be different things. So we do line. That just makes it really specific as to what it means. So it's just it's basically like a symbol. So from this thing, all those ones there are like you're listing all of the categories that fit in. Just right. So you just do because R was yeah, just a cube here. Okay, but if it's also just a positive whole number, that means it's natural. That means it's natural. So anytime you go here, so if you go here, that means it's N and W and C and Q. All. Because natural numbers are inside the numbers, which is inside the business. Yeah, so if it's I, you would write I and C and Q. Correct. Yep. Only three of them. Yeah. Yes, and an integer is only they're irrational all by itself, so irrational is only true. Yep.